So again, what do we have? We have that if we have this matrix A, the determinant is a scalar, and if the determinant of A is 0, it's not invertible, and A inverse does not exist. If the determinant of A is not 0, it is invertible, and the A inverse does exist. So that means if I've got this matrix A and I want to find its inverse, or I want to work with it, if I take the determinant, that tells me whether or not it's okay to proceed and go forward and get the inverse of this, because it's out there. If the determinant is 0, there's no point in even trying. Okay, so there's some other nice properties of this thing. One thing is that the determinant of the product of two matrices, and I got to be careful here, this is only true if both A and B are square matrices with the same dimensions. So the determinant of A times B is the determinant of A times the determinant of B, which is nice, is if I can figure out the determinant of A and the determinant of B separately, I don't have to do this multiplication. I'm not going to prove this, but I'm going to try to give the general idea of why this is true. So if I have A times B, let me think of A in terms of the first row, the second row, on down to the nth row. And now I think of B in terms of the columns. To do this matrix multiply, what am I going to do? I'm going to go across row 1 and then down B1, and that's going to give me that entry there. For this entry here, I'm going to go across row 1 and down B2 and the same thing. What's that? I'm using R1 for every operation. So basically what I'm doing there is I'm doing a row replacement, right? So if this was a 1, that's simply a row replacement, and it would not change the determinant. But if that's not 1, it's going to be the same thing as like multiplying through, and that will change the matrix. So the only thing that's really going on there is what's happening with the diagonal. The same thing is going to be true with R2 on down for all these other entries. And if you want to prove this result, you basically take advantage of the idea that A times B is you're really doing row operations and row scaling. And if you go through and do everything, you basically are going to show that you can keep track of the determinant of this, the determinant of that, and the determinant of that, you can get the same thing. So as a quick example, if I have two matrices, let's see, if I were to do the matrix multiplication, so I'd have 4 plus 9 is 13, 1 plus 3 is 4, I have minus 8 plus 3 is minus 5, minus 2 plus 1 is minus 1. So let's see, so what's the determinant of this? This is going to be 1 minus a minus 6, so that's going to be 7. This is going to be 4 minus 3 is 1, so the determinant of that product is 7. If I come here, what I'm going to have? I'm going to have minus 13 minus and minus 20, which is 7. All right, so if I have these two matrices and I need to determine the determinant of their product, I don't have to go through and do that. Another thing to note here is this. If I have A times B, then if I want to know is the product invertible, if the determinant of A is 0 or the determinant of B is 0, it's not invertible because the determinant of the product would be this times determinant of A times the determinant of B. And you can extend that idea to 3, right? So if I take the determinant of A, B, C, oops, that's going to be the determinant of A times the determinant of BC. But the determinant of BC is going to be the determinant of B times the determinant of C. So if any one of these matrices, if the determinant of any one matrix is 0, then when I take the product of all three, the product will not be invertible. And you can extend this to 4, 5, and 6 matrices. And you can play games like this. Suppose I want the determinant of A to the n. So if I have the determinant of A, and then I look at the determinant of A squared, I can think of A squared as A times A. But from my previous property, this is the determinant of A times the determinant of A. So that's just the determinant of A quantity squared. Now if I look at determinant of A cubed, that's A times A squared. So that's determinant of A times the determinant of A squared. But I just said determinant of A squared is determinant of A quantity squared. So this will be the determinant of A cubed. And I can do now the same thing with determinant of A to the fourth. That's the determinant of A times the determinant, sorry, this is going to be the determinant of A times A cubed. I can break this out now as the determinant of A times the determinant of that. So I leave the determinant of alone. Determinant of A alone. Determinant of A cubed I just decided was determinant of A quantity cubed. So that's going to be the determinant of A quantity to the fourth. And I can do this for determinant of A fifth, determinant of A to the sixth, and on down, and just keep going. If A is invertible, okay, this is kind of redundant. If it's invertible, it has to be a square matrix. Then I have this. Why is this? So if I have A times A inverse, I know that's the identity matrix. And now if I take the determinant of the product, that has to be the determinant of the identity matrix, which I know is 1. Okay, now again, I'm assuming since A is invertible, all these things exist, and this is important, the determinant of A is not 0. I can break this up into two pieces. So this is the determinant of the first matrix times the determinant of the second matrix. This is what I am after. I want to find that. I know this is not 0 because it's invertible. So the determinant of A inverse is just 1 over determinant of A, which I know is well defined. Okay. All right, last thing we're going to look at here is this idea of the transpose. Then we'll look at what this means for the determinant. What do we do for a transpose? The idea of a transpose is this. And notice the notation here. I've used the T up here like it's a superscript. This means I'm going to form a new matrix where the first row becomes this first column of the new matrix. And then the second row will be the second row, or sorry, second column. Careful, that's a -1 of the new matrix. And then the third row will be the third column of this matrix. So if this is the matrix A transpose is that. Okay, just as another example, that's a matrix B transpose. I'm going to go across this. So the first row is 1, 4. That becomes my new first column. second row is 7, 2. That becomes the second column. And that's the transpose of that matrix. And notice this does not have to be a square matrix. So this matrix is 3 by 5. The transpose is 5 by 3. Okay. One property that we have for the transpose is if I take A times B and then transpose that result, that's the same thing as taking B transpose times A transpose. So let me be a little careful here. So I've got a matrix A. This is going to be n by m. So that means that B has to be m by k, like that. So let's see. And the way we show this, I'm going to kind of sketch this out, but we find the ith row, we're going to find the ith row and jth column of this thing. When we transpose it, that new result's going to be in the jth row and ith column of the final thing. And then we find this multiple and we find the jth row and ith column of that and see if they're the same. So let's see. So if I think of A times B, let me think of this as the first row of A, the second row of A, on down till I get down to the nth row of A. Then for B, I'm going to have the first column of B, second column of B, all the way down to the kth column of B. And so what am I after? I'm after the ith row and the jth column. So I want to know, what is that number? So that number is, I'm going to go across the ith row of A, and then I'm going to multiply by the jth column of B. Right, so I'm going to go across the ith row there and the jth column of there. So I'm going to go element by element, this times this plus this times this, and go all the way down and add them up. So I'm basically looking at the product of Ri and Bj, and this is going to be the ith row and jth column of AB. So therefore, if I take AB transpose, this will be the jth row and ith column. So now let's look at B transpose, A transpose. So B transpose, the first row is going to be the first column of B. The second row is going to be the second column of B, and I go on down that way. So this whole thing is B transpose. Now I need to find A transpose. So for A transpose, the first column is going to be the first row of A. The second column is going to be the second row of A. I keep going like that. And so now what is it I'm after? I'm after the jth row and the ith column. I want to know, what is that element? So that's going to come across the jth row of B transpose. And down the ith column of A transpose, like that. And if I do the product going across there and down there, notice that's exactly the same thing here. Right? I'm just switching the order. And this is the same. So we get that if I take A times B and I transpose it, that's the same thing as taking B transpose times A transpose. All right, and we're going to have this, is that if I take the transpose of a matrix and take its determinant, I don't change it. This is very kind of technical and detailed, but the basic idea is this, is that if I think of this as the columns, And if I take the transpose, this first row is the first column, second row is the second column, and you can go through and keep track of the row operations that's going to convert this to this, and after you do all the row operations and everything cancels out and you get the same result.